What is that? Oh, nothing. I'm just studying for tomorrow's exam. Could you help me? Yeah. Mm, yeah. Matter is any substances that has mass and takes up space. Everything is made of matter, so any objects that you can name consist of matter. So, does this book a matter? Yes, for it has a mass and take up space, which we can see here on the table is occupying this area. So therefore, it is a matter. Ah, but does matter change? Yes, matter changes, but there is no new matter. Huh? It is what we call the law of conservation of mass, and it states that the matter cannot be created or destroyed in a chemical reaction. So the mass of the product equals the mass of the reactant. The reactant is the chemical interaction of two or more elements to make a new substance that is formed as a result of chemical reaction. Matter and its corresponding mass may not be able to be created or destroyed, but can change forms to another substances like liquid, gases, and solids. From the word conserve, it means it maintains or stays the same. The composition of a liquid substance does not change even it changes into a solid form. Now, these compositions are classified into categories: pure substances and mixture. A pure substance is a form of matter that has a consistent composition and properties that are constant throughout the sample, while a material that is composed of two or more substances is a mixture. Now we are on energy. So, potential energy is a energy stored in an object. If an object does not move or is still, it means it has a potential energy. It is known to have a potential energy because once it is released, it does a lot of work. On the other hand, kinetic energy is an energy that is in motion or the object is moving. For instance, a water at the top of a waterfall or a dam has a potential energy because of its position. And when it flows downwards through the generators, it has a kinetic energy. And that energy can be used to do work and converts into a electrical energy and produces electricity which we are using here in the house. Just remember, energy can neither be destroyed nor created, but it can transform from one form of energy to another. Now, what if an object has a potential energy and a kinetic energy? It becomes or it is called mechanical energy. For instance, a deconstruction ball. If the ball is still and doesn't move, it has a potential energy. But when it moves, it has a kinetic energy. And when it hits in a wall and creates a big damage, that is when we are calling that a mechanical energy. Going back to matters, it says here that matters has different states. So, yes, the different states of matter is solid, liquid, gas, and sometimes other considered the plasma. In solid, the molecules that make up a solid are arranged in regular repeating patterns. They are held firmly in place but can vibrate within a limited area. While in liquid, the molecules that make up a liquid flows easily around one another. They are kept from flying apart by attractive forces between them. Liquids assumes the shape of their containers, and on gases, the molecules that make up a gas fly in all directions at great speeds. They are so far apart that attractive forces between them are insignificant. And on the plasma, at the very high temperatures of the stars, atoms lose their electrons. The mixtures of electrons and nuclei that results in the plasma state of matter. Now, in what ways does this states of matter change from one form to another? The process of which a solid becomes liquid is called melting, and the process when liquid turns into a gas is called vaporization, while the process when gas turns into plasma is called ionization. Now, if the process is backwards, the plasma turning into a gas is called deionization, and if gas turns into a liquid, it is called condensation, while the process of liquid turning into a solid is called freezing. Oh my, thank you very much for your help. So much appreciated. Are you free right now? If you are, let's go watch a movie first.
Yes.
Come, here, sit. This is a very good series though. Very educational, especially in the field of chemistry.
Oh, finally, you're here.
I just want you to know that these elements has variations. Though some of it might look the same, but each of it has distinction from their physical to chemical properties. So, do you want to know what is physical and chemical properties? Well, physical properties is any characteristic that determined without changing the substance's or chemical identity, while chemical property is determined only by changing a substance's molecular structure. We will go into details on both properties, but first, we will talk about physical properties. So physical properties are divided into two smaller parts. These are intensive property and expansive property. Intensive property includes color density, boiling point, and melting point. Now, let us talk about water as an example. A 10 kilogram of water in the pile is color blue. If we add another 5 kilogram of water, the water is still color blue. Even the density of the 10 kilogram water is the same as the density of 15 kilogram of water. In addition, the boiling and melting point of the 10 kilogram of water is the same as the 15 kilogram of water. In the other words, intensive properties as those properties that does not change even if the amount of the substance is small or larger. Well, extensive property on the other hand includes mass, volume. For example, if a 5 kilogram of water is added to the 10 kilogram of water in the pile, it will result to 15 kilogram of water. Hence, the mass of the water change so as its volume becomes larger. Next is chemical property. A change in the substance chemical structure is observed. This includes the heat of combustion, which is the energy released when a compound undergo burning with oxygen, and flammability, which refers to whether a compound will burn when exposed to a flame. Substance can also undergo physical or chemical change. For example, ice. When the ice is exposed in the room temperature, it will become liquid. But when you put it again into the freezer, it will go back as ice. So this is an example of physical change. In simple, it is just a change in physical state. It can go back to its original state. When you are burning wood for you to cook, then the wood turn into ashes. But you cannot turn ashes into wood. This is an example of chemical change. In simple terms, there is a change in atomic structure and gonna go back to its original state. So, do you know what is the differences between physical and chemical properties and physical and chemical change? Now it's your turn.
Oh, thank you very much for that. Now that I am going to prepare for work. I should prepare now because in 5 minutes there will be a class. Oh, so good day class. Today we start our first actual lesson on chemistry. I am your new professor, Vincent Marco Devesa. The topic that I will be discussing today is about mixtures, substance, compounds, and elements. But before we dive into the topic, let me show you an illustration in order for us to conceptualize the subject. So we will discuss the terms from top to bottom based on the illustration that I've shown you. So first is matter. What is matter? Matter is anything that occupies space and has mass. Matter can be made up with either pure substance or mixture. So, under matter, we have pure substance. So, what is the definition and classification of pure substance? Pure substance is a single kind of matter that cannot be separated into other kinds of matter by any physical means. This can be either an element or a compound that has the same type of molecular characteristics. But to ensure that something is a pure substance, we need to remember that it must contain exactly the same thing with a fixed definitive set of properties. So an element is a substance that cannot be broken down in any means. You might be remembering in the definition of pure substance that pure substance cannot be separated in any physical means. But in the case of elements, it is unbreakable chemically and physically. Elements are defined by the number of protons they possess. Atoms of an element all have the same number of protons, but they can have different numbers of electrons and neutrons. Elements, remember these elements consist of one atom only. There are 118 known elements as of today. Each of the 118 known elements has its own chemical symbol, which can be observed in the periodic table here. So to demonstrate you actually, now we have a sample element here called phosphorus. This chemical symbol is P. It can be found in the head of matches. So here. On the other hand, a compound is a substance that results from a combination of two or more different chemical elements. A compound contains atoms of different elements chemically combined together in a fixed ratio. It can be broken down to individual elements through chemical methods or reactions such as hydrolysis and the like, but not physical methods or change. Water, sodium chloride, sodium bicarbonate, and hydrochloric acid are the examples of compounds. Why is it that compounds are still considered pure substances despite of its combination of two or more different elements? The reason for that is compounds are chemically bonded and it is arranged in a fixed ratio. It is unlike the mixture, which is physically bonded only. To prove that compounds can be only broken down only with chemical reactions or methods, let me demonstrate this cup of water to physical change or methods. It will undergo boiling, freezing, and filtering. So first we have boiling. So I boiled earlier a cup of water which some of the water became water vapor, but still it is considered H2O even though the water became gas. But even though we boiled the water, it will eventually come back as rain and it is still considered as H2O. So in freezing, we have here a solid ice. Even though that the water H2O became solid or changed the phase of matter, it is considered as solid ice even though it has a physical change. So third one is filtering. When I filter a cup of water into another which has a filter system, in the end it is still H2O. It is impossible to physically separate the compounds, which is water is one of the examples. So this further proves my point that whatever physical separation we do, it is indeed impossible. It can prove that my statement earlier that pure substances like compounds can be broken down only through chemical means. So next, I will show you some examples of chemical change in pure substances. Here we have rust. Rust is the result of corroding steel after the iron particles have been exposed to oxygen and moisture. When steel is exposed to water, the iron particles are lost to the water acidic electrolytes. The process of iron oxidation is considered as chemical change because the chemical property of iron is that is capable of combining with oxygen to form iron oxide, the chemical name of rust. Meaning that due to the process of rusting or corroding steel, the ordinary steel nail became an iron oxide nail. Later on, we will conduct a hydrolysis experiment. But before that, let's discuss mixture and its kinds. So, mixture is a combination of two or more substances or compounds which are not chemically bonded. It can be only separated or broken down through physical means. There are two types of mixture, which is homogeneous mixture and heterogeneous mixture. But first, we will tackle homogeneous mixture first. So, homogeneous mixture can be broken down into two Greek root words, homo and geneus. Homo means the same, while geneus means kind, therefore translating to the same kind. It is also known as solution. It is a type of mixture in which the components mixed are uniformly distributed throughout the mixture. In other words, they are uniform throughout. As you can see, there are no visible parts in this mixture. Therefore, we cannot judge a homogeneous mixture by just seeing it firsthand. At first, you might think that this is only water, but I actually mixed salt in there earlier, making it salt water, which is the combination of sodium chloride and H2O, making it a homogeneous mixture or not pure substance. So, heterogeneous mixture can be broken down to two Greek words, which is hetero means different, while geneus means kind. It is therefore making it translate to different kind, which is almost the exact opposite of homogeneous. It is a type of mixture in which all the components are completely mixed and all the particles can be seen under a microscope. We can easily identify the components and more than one face can be seen by the naked eye, unlike the homogeneous mixture due to its unrecognizable parts. So let's try here to further prove my statement. So as you can see, you can clearly see the difference or the division between the water and the oil. Since water is more dense than oil, making it submerged, while oil is less dense than water, making it rise. So therefore, we can prove that oil on water mixture is heterogeneous, not homogeneous, unlike the salt water, which is almost unrecognizable where the salt and the water is because it is uniformly mixed. Unlike oil and water, you can see a clear division or a clear recognizable parts, making it more easier to identify than homogeneous. So here are some examples of homogeneous mixture. Let me show you. So first we have sugar water, which is the combination of sugar and water. Let's see if we can prove that homogeneous are almost cannot be identified by its unrecognizable parts. So these So the sugar is almost unrecognizable because it is completely uniformly mixed in water, making it sugar water, which is a homogeneous mixture. Therefore, my statement is correct that sugar water is homogeneous. Next, we have salt water. Salt water is the combination of sodium chloride and water. And again, my statement is correct. It is homogeneous mixture since there are almost no unrecognizable parts. As you can see, it is almost like water, but it is not. It is salt water. So again, to show you another example, wait. We have here a water and acetic acid, or known as vinegar. Let's try to see if there are any recognizable parts. So let me mix it first. And again, for the third time, my example is correct. Acetic acid plus water is homogeneous mixture because it is almost unrecognizable. You cannot even see the acetic acid or water or their particles are. You cannot see it because it's now considered as vinegar water or acidic acid plus water. So that's it for my examples for homogeneous mixture. Remember, in homogeneous mixture, it must be, the parts shall not be unrecognizable, and the particles shall be uniformly distributed or arranged. Remember the statement regarding mixtures that it can be broken down into physical means or methods. So, in order to prove it in front of you, we'll conduct a little demonstration. You might be remembering that the statement regarding mixtures can be broken down to physical means. In order for it to prove it in front of you, we'll conduct a little demonstration. I'll remember that the boiling water I showed you earlier. So I boiled it again to ensure that all the water vapor can go to the atmosphere. So here's the result. You can see that there are little salt particles that are present, that is the remnant of the boiling water. This further proves that we can physically separate the salt water if we can boil it down until all the water vapor goes to the atmosphere. So therefore, the evidence shown in the experiment proves my statement is again correct, due to the fact that we can physically separate salt from water through boiling. Some examples of heterogeneous mixture. So first, again, I will show you again, oil and water. To prove that it is heterogeneous, you can see that you can identify which is the oil and which is the water, which we can recognize it because of its visible and recognizable parts. Therefore, we can prove that it is heterogeneous mixture. And also, heterogeneous mixture are not uniform when it comes to particles. So next, here's another of heterogeneous mixture. I mixed rocks and water. As you can see, it is very obvious that the rocks are clearly submerged because it is more dense than water. This further proves that it is also heterogeneous mixture because we can identify where is the rock and where is the water here. So class, in order to summarize the class, there are things to remember here. First, that matter is anything that occupies space and has mass. Pure substance is a single kind of matter that cannot be separated into other kinds of matter by any physical means. An element is a substance that cannot be broken down in any means. Elements consist of one atom only, while a compound is a substance that results from a combination of two or more different chemical elements. And remember that compounds can be broken down through chemical means but not physical. Mixture is a combination of two or more substances or compounds which are physically bonded. It can be only separated or broken down through physical means. Homogeneous mixture is the mixture in which the components mixed are uniformly distributed throughout the mixture. There are no visible parts. Heterogeneous mixture is a type of mixture in which all the components are completely mixed, meaning that it is not arranged or uniform in such a way. You can easily identify its components and more than one phase can be seen by the naked eye. Okay, now we shall continue our experiment regarding the chemical reaction in water, which is a compound under pure substance. Here are my materials needed in order for me to experiment hydrolysis. First is a 9-volt battery. Next is acetic acid to help with the process of hydrolysis, and salt. These two are used to put in water to help the hydrolysis process even faster. And next we have a glass of water with two spoons serves as a conductor. So how it really works. I will connect the battery here into the tip of the spoons, making it to conduct hydrolysis. But before that, let me explain hydrolysis first. Hydrolysis reactions are the reverse of condensation reactions. In a hydrolysis reaction, a larger molecule forms two or more smaller molecules and water is consumed as a reactant. Hydro means water and lysis is break. It involves adding water to one large molecule to break it into smaller molecules. Remember, as a safety precaution, chlorine gas is dangerous when inhaled in large amounts, and corrosive alkaline can burn your skin. Ensure that the place that the experiment will be conducted is well ventilated or outside before trying the experiment. So, I will put the salt first to help with the hydrolysis process. Wait. Let me mix it a bit for a while. Steady. And next, I will add acetic acid or suka. It's a little bit more. Okay. Now we will conduct the experiment if it is really working or not. So let's put the 9-volt battery into the tips of the spoons. Wait. And reminder that avoid the spoons colliding with each other because it will create a circuit making hydrolysis the experiment flux. So we have here the as you can see, there are bubbles. Nabidyo yung bubbles. As you can see, the bubbles are already existent, making it sodium hydroxide. Okay, why my experiment is not working anymore? It already worked earlier. Probably my computations and measurements are wrong. I need help. Jay, I need your help. My experiment went wrong. It's like my computations and measurements. Can you help me?
Yes, sure. Sure, doctor, sure.
We make measurement all the time in our daily lives without even realizing it. When we walk, we usually measure the proximity of objects in our environment. When we pick an item, we measure its weight and adjust our muscular response according to our initial estimates. Measurements are observations of a quantitative nature that are taken by some forms of equipment. Some equipment, like our five senses, can give us very approximate measurements, while other technology like scales provide more exact measurement. Many of instruments are used to measure and study our chemical world. Some of the common quantities we measure in chemistry are distance, volume, mass, time, velocity, temperature, density, pressure, amount of concentration, energy, and electric charges. In this, we will investigate how various methods of measurement are used to study the chemical nature of matter. Measurement is a fundamental aspect of science and chemistry. Our understanding of chemical world would not be possible if we did not compare, contrast, categorize, and analyze our observations to obtain the information we have about chemical substances. Let's consider water as an example. Many of the qualitative non-numerical properties of water, including its taste, smell, textures, and color, can be observed using our senses. We can also measure quantitative properties of water by using equipment. For example, we can use thermometer to measure water boiling point in degrees Celsius, or a measuring cup to measure the volume of a given liquid. There can be different units that are used to measure the same physics quantity. For example, temperature can be expressed in degrees Fahrenheit, degrees Celsius, or degrees Kelvin. No one set of units is more correct than the other. However, as we begin measuring, calculating, and sharing measurement, we will want a standard set of values that we and others can use. An international governing body has developed a metric system of units of measurement for scientists called the SI units, which is the System International Units. Some of these physical quantity, which is the length, mass, time, temperature, electric current, amount of substance, luminous intensity. While in the metric system, we have a meter, kilogram, seconds, Kelvin, ampere, mole, and candela. With the base unit listed in this, we can describe many physical details of a given chemical substance. Base units are measurements that have their own independent scales and cannot be expressed in terms of other base units. All other measurement quantities such as volume, force, and energy can be derived from these 7 base units. For instance, volume is calculated by multiplying together 3 different lengths, which is height, width, and depth. We call this 3 combinations of base units is derived units. Some of example is, we have the physical quantities, area. The name of SI unit is square meter, abbreviation is M2. Volume, cubic meter. Speed velocity is meter per second. Acceleration, meter per second squared. Force, Newton, mass and acceleration. Mass density, kilogram per cubic meter. And energy is joule, force, and distance. You probably won't use electric current and luminous intensity in general chemistry, and will only rarely use time. The other 4 properties, which is the length, mass, temperature, amount of substances, or amount of substance, are used regularly. Every other unit is derived from the base unit and appropriate mathematics. One unit that is commonly used but isn't fundamental is a unit for volume. Consider this box. This is a box, but I'm not good in drawing, but this is a box. If we want to find the volume of this box, we multiply the width. This is the width and the length. We multiply the width times the length times the height. This is height. height. And to get the volume, we will use the V length times width times height. The volume unit will be cubic units of distance if the length, width, and height were measured in meters. Then the volume unit will be meters times meters equals meters. Volume is a derived unit and you will encounter many other derived units. So for now, we were going to tackle about the unit factor, which is the dimensional analysis. So dimensional analysis is a calculation procedures allowing us to express calculated values with proper units. You have already seen a couple of examples of how new units are produced, right, Doctor? And basically, units follow the same rule of arithmetic that numbers follow, which is the additions and subtractions. The units of the quantities being added or subtracted must be identical. Subtracting, which, for example, subtracting 4 apples from 9 apples give us 5 apples. So 9 apples, 3. 9 apples, 4 apples equals 5 apples. Subtracting 4 apples from 9 apples is a meaningless operation. Sometimes we will be given values having identical units. Other times we will have to change the units of one or more values before we can add or subtract. We can change unit using conversion factors. A conversion factors is the ratio of two equivalent quantities. For example, 1 kilogram is equal to 1,000 grams. Whether we measure mass in kilogram or in grams, we can change from the grams to kilograms or kilograms to grams using the proper conversion factors. From any pairs of exactly equivalent quantities, two conversion factors can be written in 1 kilogram or 1,000 grams or 1,000 grams or 1 kilogram. Both of these conversion factors are equally correct. Which conversion factors do we use in a problem? The choice depends on the units of the quantity we want to convert. If I want to convert 7 kilograms into grams, the conversion factors I use is 1,000 grams in or 1 kilogram. I reform the following calculation. For example, 7 kilograms times 1,000 grams and 1 kilogram is equals to 7,000 grams. This example shows the most important idea in using conversion factors. Select the conversion factors that has the desired unit on top. Then when you multiply your starting quantity by conversion factors, the desired units will carry through the calculation. Sometimes several conversion factors must be used before the final result is determined. So to become more understandable, the unit factor method or dimensional analysis uses a conversion factor to change the unit in an amount into an equivalent quantity expressed with a different unit. For example, a conversion factor could be used to convert 3.55 meters to centimeters. Perhaps you can determine the answer to this particular problem in your head. However, the conversions that will be required to this will become increasingly complex. So I hope I help you doctors in your problems, and I will give you these notes so that in your next experiment it will be successful. So here it is.
Thank you for your help.